which also has in it symbolic constants for kind type parameters, and here are two int 64-bit and real 64-bit. So if I wanted an 8-byte integer, I would declare integer kind equals int64, and that would give me, this is telling the compiler I want this to be an 8-byte integer. Likewise 8-byte real. For complex, it's the parameter refers to the individual components, so this is 8 bytes for both real part and 8 bytes for imaginary part. So those constants are provided by this ISO Fortran env thing, which the implementation must provide. So standard says a Fortran implementation must provide at least one integer precision with decimal exponent range so big. I think almost all implementations will provide two integer kinds, typically 4 bytes and 8 bytes. Again, if you're coming from C, C++, note all integers in Fortran are signed integers. There's no equivalent of the sort of C unsigned types. Likewise for real, implementation must provide at least one so-called default precision and one extended precision, which is more bigger in some sense than the default precision. Again, these are typically 4 bytes and 8 bytes. The extended precision is sometimes referred to as double precision, and one is actually allowed to make declarations with the double precision statement, but the modern preferred form is just to use real with a kind type parameter. So that's the formal statement so for numeric types. Again, if you look at this formal description, things like this kind equals in the parenthesis are optional, so there's quite an elastic range of options for exactly how you write these declarations. A reasonably concise form is just to stick the kind type parameter in parenthesis before the double colon, which is the variable list. Okay, so there's a bit of an exercise here with two programs where I have used different kind type parameters. I'll give you a couple of minutes to have a go at that if you haven't done so already. Okay, so again, your mileage may vary a little bit here depending on what compiler you have, because this is free format. If we move to using the GNU compiler, if you try the program that is using the 4-byte versions, you should see you're getting about 7 or 8 decimal places of precision in the output. If you use the version that uses the 8-byte ones, you're getting about 15 or whatever it is decimal places of precision in the output, and that's the 4-byte and 8-byte rules. So there's a question in the chat. Why does this fail? Might need to know what the failure message is. You could try 1.0. We'll come on to literals in a moment. Yes, so the E precision is usually the lower precision version, so the exponent 100 will probably overflow. You might have to do D 1D 100. Come on to literals just now. So those are variables of different forms. You can also explicitly append a kind type parameter to a literal number by using this sort of underscore notation. If you want to be sure you're getting one thing or the other. For scientific notation, there is an E form, which is the default precision, and there is a D form, which is the extended or the double precision. So that from memory, the E form will go up to about a range of exponents of about -37 to +37. The extended precision typically goes from about -300 and something to about 310 in the exponent range. Complex literals, as we've mentioned before, are just made up of 2 real parts. Okay, so in that previous example, we explicitly declared our variables with kind type parameters from this ISO Fortran env module. That's fine, but you may see slightly different things. An example of which is given here. So the first thing to note, the kind type parameters are themselves just integers. They just have an integer value. So we can use an integer variable to represent them. Furthermore, I've introduced something slightly new here. And the new thing is this so-called parameter attribute, which we've separated from here with comma parameter. So this is an instruction to the compiler to say this variable will not be changed in the course of the execution of the program. So it's a constant. So it's a bit like a const declaration in I'm going to define two kind type parameters here, and I'm going to do it by using this intrinsic function kind, and that function returns the kind type parameter of the argument. So the kind type parameter for the default precision real is the return value of that call, and the kind type parameter for the double precision or extended precision is the result of that function call. So I can then use these variables to declare new variables of a given kind. So this is the way to add parametrically the precision of your real variables. So if you have a lot of declarations of real variables, and you want to switch the kind of the whole lot of them, you can just update one statement and do it like so. You'll see that kind of thing quite frequently. So the other thing to notice here, this function kind is an intrinsic function in Fortran. We haven't included anything or imported anything or used anything to make it available. It is an intrinsic function which is part of the language, so the compiler knows what to do with it. Furthermore, you can have parameters of any, don't have to be integers, they can be different data types. So for example, one can define floating point parameter. Again, we have the definition here using the intrinsic function, the arctangent. So that's the value of pi. Note that the compiler, because this is an intrinsic function, the compiler knows what to do with that, and you can make a parameter declaration based on this calculation, as long as all the parts of that calculation are themselves intrinsic. Okay, so there's another little exercise here to have a go at, example 3. And I've allowed, I think, a couple of minutes for this, to just have a quick check of the results of this exercise. So there's a question arises from this. You will occasionally see something like this in a program. So our kind type parameters are just an integer, so this is perfectly legal. So let's have a vote. If you think that's going to be portable, put your hands up. Nobody? If you think it might be portable, not portable, yes, okay. And if you have no opinion at all, Okay, so the speculation here is this is, I would suggest, poor practice, which people sometimes get away with. There is nothing in the standard which says kind type parameter 4 must correspond to a 4-byte real, or kind type parameter 8 must correspond to an 8-byte integer. However, they usually do, but not necessarily. There may be some compilers out there, I won't name any names, but which will give you a problem with things like that. So I would probably recommend, the recommended way would be to use the symbolic values from ISO Fortran Env, which avoids any potential problems. Okay, so there's another very short exercise there. Has anybody spotted the problem there for exercise 2? Yes, okay. So there's a question perhaps about what the intention of the programmer was, but so if the intention was for this thing to be a parameter, then you should see. Let's have a go, shall we? So this is GNU. So this thing nmax has been declared as a parameter. Here at line 11, I've tried to assign a value to it. So I get an error from the compiler saying you can't do that because you've declared it a parameter, and assuming the intention of the programmer was for this to be a parameter, you would have to remove the assignment. Okay, any questions on parameters? Okay, so once you've got some numeric data, you might want to carry out some arithmetic. This is pretty much what you'd expect, I think. One has addition, subtraction, multiplication, division, and exponents, which in Fortran is this star. Syntax. So, for example, this is this statement here is A is B times C squared. Evaluated with that precedent, which is kind of what you'd expect if you sort of wrote that in mathematics, B, C squared. Otherwise, it's just operators of equal precedence are left to right. You can always, of course, use parentheses, like so, if you wish to avoid any ambiguous situations. Being Fortran, there are a large number of intrinsic functions available for basic mathematical operations, things like square root, trigonometric functions and so forth. I'm not going to provide an exhaustive list, because that's just tedious, but if there's something you want to do, you should be thinking there may be an intrinsic function to do it. So simple things like square root will work for all the numeric types, so it's perfectly acceptable to take the square root of a complex number, for example, and achieve a complex result. Some of the intrinsic functions are specific to particular types. So for example, only a complex variable has a complex conjugate, which is this function here. So if you're trying to mix arithmetic or assignments between different data types, this gives rise to promotion usually, or truncation. This may require you want to be explicit, and the mechanism to do this in Fortran, analogous to explicit casting in C, is to use some functions. So if I have declared integer I, and I want to be completely explicit in assigning that value to real variable A, I can use this real function. It takes the argument, which is the value you want to assign, and optionally also a kind type parameter of the result you want. So that is the way to get to reals, and likewise there is an int function which will return an integer value. The complex, if you want to construct a complex number from two real numbers as an assignment, as an executable statement, you can do it like so. So there's various functionality to allow you to do that. So as a something of a aside here, you'll note here real appears here as a statement in a declaration. Real is also appearing here as a function name, which is different, a different use. So there is not quite the same idea of reserved words in Fortran as you get in C and C++, for example, where that sort of thing probably wouldn't make sense. So Fortran is based on lines which are split into tokens, which are then interpreted in context. So you often get the same thing appearing in different contexts. Again, just a note on there's slightly different ways to do things. There is a slightly different way of getting hold of the real and imaginary parts of a complex variable, which is using this so-called component selector symbol, the % sign. So if you have a complex variable Z, the real part can be accessed as Z%RE for real and Z%IM for the imaginary part. We'll see this again when we get to look at structures. So there's a couple of exercises to have a go at. here. The first one is relatively short. The second two are a bit longer. Not expecting you to get through all these. You might want to have a look and have a choose one or the other. This first one with the template exercise 3 is probably slightly more familiar. Okay, so I'm going to give, I think, 5 or 10 minutes to have a go with that. And again, just please type into the chat or raise a hand if you have a question. Okay, yeah, so there's an observation in the chat. So we have a program where we define a complex variable z and ask for the square root of -1 to be assigned to z. And the output is a rather ugly not a number as the real part, and 0 as the imaginary part. Can anybody think what's going on here? And I'll give you a clue, it's on the right-hand side of the assignment. Yes, so Maurizio has got it, I think. So the statement z is the square root of -1 is something you would naturally want to say in mathematics. For the Fortran compiler, this won't quite make it, because the compiler will come along and says, I have here a square root function, and the argument is a real number, which is -1. So I'm going to go away and try and use my real square root function to compute this, and of course there is no solution in real numbers. So the answer is you actually need to give the square root a complex number as the argument. So you could either make a variable which is real -1, a complex variable which has the value of, which has the real part -1, and use that, or you can use one of these explicit, this explicit complex function to form a literal complex number. So that will then, the compiler then knows the argument to the square root is complex and should be interpreted as a complex result. Okay, hopefully people are making some progress there. So for quite a number of the exercises, here, a solution is going to appear later as a template to a later exercise. So I'll wait perhaps until a bit later to go over. If anybody wants me to go over these things, I will do so. However, we can now think about going on to the next section, which is section 1.03, which is here. Okay, so I discussed in the previous section numeric types, integer, floating point, real, and complex. The other two are logical and character. So logical types are declared logical. They can have one or two values, true or false. And in Fortran, they appear with this dot, true dot, and dot, false dot syntax. Formally, logical variables do have a kind type parameter, but it's pretty rare to actually see anybody use them. So I haven't included them here. So logical variables and expressions are typically used to control the decisions in the program based on logic. So the logical operators are this dot or, dot and dot not. And their precedence is illustrated by this expression here. If you have something like that, if you include parentheses, it is evaluated with not binding most closely there. So the other thing one might wish to do is use numeric expressions to form logical expressions using relations. So again, in Fortran, there's probably what you'd call a modern form, which is just to use the relational operators you'd expect, less than, greater than, so on. There is also an older form which is using this dot notation. You may see this in places, dot LT for less than, and so on. Equals is equals equals. Not equal to is this slash equals. If you're coming from C, don't accidentally do the C form. If you've got logical variables, the formal situation for logical equivalence is dot equivalent or dot not equivalent. Don't use equals if you're testing two logical variables against each other. The other thing to say, of course, is for things like less than are not meaningful for complex numbers. Okay, so that's logical variables and expressions. If you want to actually do some flow of control, you have it. This is the if construct. formally it looks like this. You have if logical expression, which evaluates to true or false, then if it's true, you go into the then block. There are optional 0 or more optional else ifs and an optional else if the expression is not true. A very stupid example is here. So here's my logical expressions. If I have two numeric, say integer variables, there's my logical expression. If I is less than j, I get that. Else if, then else, and so on. That should be fairly familiar from other programming languages. There's also a single clause if you can use, which just omits the then, and a single statement might look something like that. So you noticed up in this formal description, there's these optional construct names. These can be useful if you have highly nested constructs to reduce the ambiguity as to which particularly this, if you come across, if you have a very big if statement, it can help to label the end if as belonging to a statement, and this has this. This is optional. You don't need to do this, but it is available. So that kind of thing, for me, I always felt that looked slightly weird. So what I tend to do is put my label, if I do it at all, I'll put the label on a separate line here. And I've introduced here the continuation character in Fortran, which is the ampersand. So you'll remember that I said lines are significant in Fortran. So if you want to have a statement which spans more than one line, you need to tell the compiler that the line is continued. And this is done with sticking an ampersand at the end of the line, and so that's telling the compiler that that if statement there is associated, all one statement with the previous line. So it's appropriate to say at this point, standard maximum line length for Fortran is 132 characters, and if you have longer lines, you can continue almost to your heart's content to a maximum of a very large number of lines. This is incidentally often to allow no human author would be likely to write such an enormous statement, but automatic code generation does sometimes generate extremely long continuation lines, so that's can be useful. Yes, so again, something else to watch out for. If you've been watching very closely, you may note that in some places I have used end if with a space. I think elsewhere you may see end if with no space. like so. Both are acceptable, both are valid, Fortran, so it doesn't particularly matter. I think the course, apart from that example, to remind me of this issue, is using NDIF with a space. Okay, so the other form of sort of conditional construct which can be useful is select case in Fortran. This is analogous to C switch, if you're familiar with that. So this is basically taking conditional action based on the value of an expression, and different cases are dealt with in different blocks, and there's also some default action. This can be useful in some contexts. So here's again a slightly artificial example. I'll say I have a playing card which I've indicated by numbers 1 to 13. I can make a select case on that integer value and perform different actions depending on the value. You can see there's again, this is quite a flexible statement. You can have a single value or a range of values using this range colon specifier, or comma separated list of different values. And there's the default. The only other thing if you're coming from C, note there's no sort of analogy of the break statement, which is always a classic for forgetting in C, actually. I think that's why they didn't have one in Fortran. Okay, so that's logic. So logical variables can be useful for controlling the flow of the program. I'm just going to say something briefly here about character variables, which is the last kind of intrinsic data type. I'm going to say a bit more about strings later on. But for the time being, I think that looks like a typo. If somebody's zealous, you might want to make a pull request to correct that. Characters or strings are declared with this form, in which there is a length specifier in parentheses. Characters or strings are allowed to be a parameter, which is whatever is the assignment over here, in which case the length of the string can be worked out automatically by the compiler, and you don't have to specify it. For a general declaration, one needs to specify how many characters you've got. In this case, 5 and 6. Literals are there's some examples over here in the initializations. Literal strings can be either enclosed in double quotes, like this one, or they can be enclosed in single quotes, like that one. If you want to have a quotation character in the string itself, You can either have the other type of quote, if you see what I mean, in this example, inside, or you can do it like so, which will give you a double quote in the string. There's not quite this same notion of the escape character you have in C strings. So if you want quotes in a string, you have to do something like this. Again, formally, characters have a kind type parameter, but you don't often see it included. Must have a length specification of some form. And again, the caution here is, again, for backwards compatibility reasons, there are various different forms of these declarations you may see. But I'll try to stick to this I would claim is the modern form. Just a couple of things to note here. If you want to concatenate two strings together in the code, there's this string concatenation operator, which is double slash. And the other thing you can note, you can use this kind of range notation to extract a substring from a string. So that string 1, 2 would be the first two characters of whatever value the string had. As I say, I will come back to strings in more detail later. Okay, so I think there's a bit of an example you can have a go with just to check out the what actually appears from these declarations here. And there's a bit of an exercise to have a go with some logic, which is the old chestnut of solving a quadratic equation. So we need to compute the discriminant, and based on the value of the discriminant, you can take the appropriate action. So that's just a bit of an exercise in logic and using the if construct. Any questions on that? There's a question about is the default case mandatory? That's a good question, actually. I think you must, in C, you must have a default case. That may be a true statement. I'm not. I'd have to try it out to be sure.
I can just pitch in here. I have used it without.
Yes, okay.
Debugging purposes.
So, yes, as I say, as Alexi says, probably you should, in terms of having a robust program which can respond to error, probably should have a default. So at that point, so if you need to consult, maybe we're saying you need to consult a reference in Fortran. The key reference is this one, which I'm holding up in front of the camera now. Modern Fortran explained by Michael Metcalf, John Reed, and Malcolm Cohen. So Fortran is one area where it is, I couldn't imagine trying to be a Fortran programmer without a book. So if you want to be serious about Fortran, this book is almost essential, I would say. I think the latest edition is 2018. This one is green, which is, I think, a red color. This one is, this is 2015, which is green. Okay, I'll shut up and give you 5 minutes or so to have a look at those exercises. Okay, hopefully people are making a bit of progress. Any questions arising? If not, just before, in the 15 minutes or so before the lunch break, we'll go on to section 2.01, which is loops. So here we go. As well as logic and conditional statements, the other main mechanism one has as a programmer to control what happens is some kind of iteration. And in Fortran, this is the do construct, which is somewhat analogous to for in C-like languages. So the most simple form is just to have a structured block, which is do, end do. Again, end do can have a space or no space. You may see one or either, and that will just go around in circles forever, which may not be very useful. So if we wish to do something with this, we better have some control. So here's an example. Again, this code is available as an example in this directory, so you can mess about with it if you like. So I've defined an integer I with some initial value. I have an iteration. I'm going to increment I by 1 each time, and I'm going to have a condition here. So if remainder after division by 2 is 0, cycle. So this is the command to go to immediately to the next iteration, please. So this is a bit like continue in C style languages. The mod function here is remainder after division. And there's another condition here which calls exit, which is get out of the loop completely, which is a bit more like break in C-like languages. So cycle and exit are the way to control iterations of the loop. Again, loops may be nested and they may have names. So I've got some example here. There's an outer loop with a label. There's an inner loop with a label. And if you want to be completely unambiguous, you can refer to the label in the command. So, for example, there I want to exit the outer loop. If you don't have a label, then an exit or a cycle will bind to the innermost construct. So it would be the inner loop if you didn't have a label there. So those can be useful. So those kind of loops you see sometimes more commonly in scientific computing. We have control with iteration and a loop control variable. So the syntax for the do loop is we have an integer loop control variable I, which we've declared, and we specify a lower bound, an upper bound, and optionally a stride. So that should give us a certain number of iterations of that loop. Formally, again, that's the situation. So the loop control, as I say, is the lower bound, the upper bound, and optionally a stride. And if you know those three things, you can you can know ahead of time the exact number of iterations you will have. So that number of iterations may be 0. Also, there are conditions on this. If you have a stride, it must be non-zero. Those are the only real conditions. Otherwise, the values can be anything you like. So as a quick thought exercise, or you can try and confirm with the example in the code how many iterations are you going to get in each of these three examples. The first one is hopefully not too difficult, unless you're coming from Python. So anybody want to hazard a guess as to how many iterations we're going to get in the first case here? No pressure. So if you wish to actually work it out, you can go up to this expression. The stride, because it's not explicit, it must be 1. So if the upper bound is 10, the lower bound is 1, and the stride is 1, then hopefully we're going to get 10 iterations of that loop. There's no funny don't do the last iteration like you have in Python. The other idiomatic Fortran thing here is Fortran being written for humans tends to count in natural numbers. Typically one starts counting at 1 in Fortran, not 0. Anybody want to have a go? Gaz, anybody? Want to have a guess at that or work it out? Yep, 0 there, I think. Yeah, not yeah, okay. Not an error. You can have. What is the screen? So this one, this is perfectly valid. You can have one lower bound of 1, upper bound of 10, and a stride of -2. That's valid. You'll simply get no iterations if you can work that out. If you go back to this statement, you should find that that comes out, because you've got a negative stride, that will come out to be negative, and your maximum of 0 and something negative will be 0. The last one is probably slightly more sensible. There you should go 10, 8, 6, 4, 2. So 5 iterations. You can run that program just to check. So the other thing to note about loops in Fortran is we assume we have declared here this variable I. So the scope of that variable I exists beyond the end of the loop. So that variable has a value beyond the lifetime of the loop. But you want to be, good practice suggests you don't want to use it after the end of the loop to avoid any surprises. Okay, so that's loops. So this is often used a great deal, of course, in real programs. So there's a bit of practice here in trying to introduce some iterations into these calculations we did in the previous exercise. So you can either use, you can either just continue using whatever solution you've come up with, or there's a new template in the current directory with the solution to the previous exercise, I hope. So, so again, you don't have to do, but you can choose one or other of those. You don't have to do both. Or you can do both if you want, I don't mind. Given I've allowed 5 minutes for that, that will take us up to lunch. So I'm going to shut up now. I will sit around here for 5 minutes to check if anybody has any questions, but then we'll probably finish for lunch.